Hello and welcome to the machine learning series. In this video, we will be learning about linear discrimination. Here, first we will see what is linear discrimination and we'll find its examples. Then we will look for the criteria that the linear discrimination uses while its execution. Further, we will see some of the merits and demerits of linear discrimination. Then we will finally wrap up our discussion after having a glance on the areas where linear discrimination finds its application. So, what is linear discriminant analysis in machine learning? Linear discriminant analysis or normal discriminant analysis is a dimensionality reduction technique which is commonly used for the supervised classification problems. It is used for modeling differences in groups, that is separating two or more classes. It is used to project the features in higher dimension space into a lower dimension space. Let's say we have two classes and we need to separate them efficiently. Classes can have multiple features. Using only a single feature to classify them may result in some overlapping as shown in the below figure. So we will keep on increasing the number of features for the proper classification. Suppose we have two sets of data points belonging to two different classes that we want to classify. As shown in the given 2D graph, when the data points are plotted on the 2D plane, there is no straight line that can separate the two classes of the data points completely. Hence, in this case, LDA or linear discriminant analysis is used, which reduces the 2D graph into a 1D graph in order to maximize the separability between the two classes. Now let's have a look at the criteria used by linear discrimination. Linear discriminant analysis uses both the axes x and y to create a new axis and projects data onto a new axis in a way to maximize the separation of the two categories and hence reducing the 2D graph into a 1D graph. Two criteria are used by LDA to create a new axis are maximize the distance between means of the two classes, and the second one is minimize the variation within each class. The graph we saw before, it can be seen that a new axis, that is in red, is generated and plotted in the 2D graph such that it maximizes the distance between the means of the two classes and minimizes the variation within each class. We can once more have a look at the graph. Okay. So moving on, in simple terms, this newly generated axis increases the separation between the data points of the two classes. After generating this new axis using the above mentioned criteria, all the data points of the classes are plotted on this new axis and are shown in the figure given below. The 2D graph is now converted into a 1D graph. Now, what are the limitations of linear discrimination? Linear discriminant analysis fails when the mean of the distributions are shared, as it becomes impossible for LDA to find a new axis that makes both the classes linearly separable. In such cases, we use non-linear discriminant analysis. Extensions to linear discrimination. The first one being quadratic discriminant analysis. Each class uses its own estimate of variance or covariance when there are multiple input variables. Second one is flexible discriminant analysis or FDA, where non-linear combinations of inputs are used such as splines. Regularized discriminant analysis RDA introduces regularization into the estimate of the variance, actually covariance, moderating the influence of different variables on LDA. Now, what are the applications of linear discrimination? The first one being face recognition. In the field of computer vision, face recognition is a very popular application in which each face is represented by a very large number of pixel values. Linear discriminant analysis is used here to reduce the number of features to a more manageable number before the process of classification. Each of the new dimensions generated is a linear combination of pixel values which form a template. The linear combinations obtained using Fisher's linear discriminant are called Fisher faces. The second application being in the medical field. In this field, linear discriminant analysis is used to classify the patient disease state as mild, moderate, or severe based upon the patient's various parameters and the medical treatment he is going through. This helps the doctors to intensify or reduce the pace of their treatment. Customer identification. Suppose we want to identify the type of customers which are most likely to buy a particular product in a shopping mall. By doing a simple question and answer survey, we can gather all the features of the customers. Here, linear discriminant analysis will help us to identify and select the features which can describe the characteristics of the group of customers that are most likely to buy that particular product in the shopping mall. And there are many more other applications as well. So this was all for this video. Thank you.